The Mill relation formula allows observers to apply the distance of an object to mathematically determine accurate locations and round adjustments. When looking through binoculars with a reticle pattern, we see marked lines allowing us to measure up to 100 mils at a time. Lines are graduated every 5 mils and marked every 10 mils. Observers must visually interpolate measurements to the nearest 1 mil when determining locations and spottings. The horizontal line is used for measurements on the ground. The vertical line is used for height of burst measurements. Applying the measurements using the Mill relation formula is based on the assumption that 1 mil in the reticle pattern will measure equal to 1 physical meter at a distance of 1,000 meters away from the observer. The mil-to-meter ratio increases as the distance increases, meaning that 1 mil in the reticle pattern will equal 2 meters at a distance of 2,000 meters, and 3 meters at a distance of 3,000 meters. The further an object is away from the observer, the greater the mil-to-meter ratio becomes. Let's take a look at a visualization of this effect. As the observer views an object through the binoculars, the mils in the reticle pattern will subtend according to the distance of the object from the observation point. Here we see the mil-to-meters ratio increase as the distance increases, demonstrating the importance of understanding how to apply the Mill relation formula. Artillery professionals use the Mill relation formula to transform visual information, such as mils in the reticulated binoculars, into physical measurements so that objects can be accurately located. The goal of the Mill relation formula is to determine W, the number of physical meters, by multiplying r, the distance from the observer to the object, times the number of mils observed. This formula is applied for lateral shift determinations, such as when identifying new data points, and for determining deviation corrections during calls for fire. Additionally, this formula is used when determining height of burst corrections. Let's take a look at an observer using this formula in action. As the target comes into view, the observer locates it and sends a call for fire. The round lands away from the target, so the observer must correct and request additional rounds. To calculate W, the number of physical meters the round must move, the observer uses the reticle pattern to determine and record the number of mils between the round and the target. Next, they must calculate R, the OT factor, by measuring the distance to the target to the nearest 100 meters and divide it by 1,000. That number is artillery expressed to the nearest whole number. Observers multiply R by the number of mils to calculate W, the number of physical meters the round must move. W is expressed to the nearest 10 meters. Let's watch as an observer uses this formula to engage a target. In this scenario, the observer is on OP Mackenzie. Their terrain sketch displays their grid location as well as known point data. Data is listed for easily visible known points and reference points. Note that reference points should be at crests or draws for easiest identification. The observer spots a target to the left of reference point Signal Mountain and uses binoculars to begin locating the target. To measure the number of mils, the observer lines up one end of the reticle pattern with reference point Signal Mountain, visually interpolates the number of mils to the nearest 1 mil, and records the data. Watch as the observer visually locates the target and scans from the edge of the reticle pattern aligned with reference point Signal Mountain, then counts and records the number of mils. As we can see, this target measures 87 mils left of reference point Signal Mountain. The observer continues to obtain target data by determining the direction to the target using a compass. By viewing the target through the sight, the observer reads the direction at the white arrow point. We can see the magnetic direction to this target is 6,000 mils. Next, the observer must determine distance to the target. Starting with known point 4, we see that the distance to the target is less than the distance to the known point. Next, the observer checks the target distance against reference point Signal Mountain and sees that it's also short of the reference point distance. Finally, the observer checks the target distance against known point 7 and notes that the distance to the target is greater than the distance to known point 7. The observer determines an approximate target distance using the recorded distances on the terrain sketch. The target distance was less than that of known point 4 and that of reference point Signal Mountain. However, the target distance was greater than the distance to known point 7. Based on this data, the observer determines that the target distance is between 1481 meters and 2312 meters away. The observer's final step in determining target data is using the MAP and OF fan. We see direction marked every 100 mils along the outside edge of the OF fan, as well as the observer's location and reference point signal mountain. The observer uses the direction obtained from the compass, 6,000 mils, and the approximated target distance as determined from the terrain sketch to identify the target area on the map. Next, they perform terrain analysis to determine a refined target distance and calculate the OT factor. The observer notes that the target is positioned on a spur, southwest of Signal Mountain. Additionally, the target is not located at a visible elevation change point. Therefore, when locating it on the map, the observer must look at the portion of the spur within the contour line. Using the map, the observer identifies Signal Mountain and identifies the appropriate spur. Remembering the observer target direction of 6,000 mils, the observer uses the OF fan to determine the target distance. The distance marker of 2,000 meters is short of the spur, and the 500-meter marker is further than the spur. Therefore, the observer must visually interpolate the target distance. Looking carefully at the map, the observer determines that the interpolated target distance is 300 meters. Now that we have all the data, let's apply it using the mil relation formula. The direction to the target is 6,000 mils, and the refined target distance is 300 meters. Our next step is to determine R by dividing the distance by 1,000, and artillery expressing to the nearest whole number to obtain our OT factor. Next, using our mils measurement, we will input the values to calculate W. R, our OT factor, times 87, our mils measurement, equals 174. We express this to the nearest 10, and now have calculated that W equals 170 physical meters. If the observer's round landed at the appropriate distance, referred to as range correct, but to the right of the target, then the observer would transmit the correction of left 170 based on the calculation from the mil relation formula. Once the correction is processed, they would get effects on their target. Observers must remember that this formula is for lateral corrections and height of burst adjustments, but is not effective for range calculations.